Okay, hopefully everyone can hear me. So I'm from Trigger.dev. I'm going to talk about how we built a real-time service that handles 20,000 updates per second. And the spoiler is that we use Electric to do that. So this is me. I'm Matt. I'm a programmer. I am the CEO and co-founder of Trigger. I love open source. So Trigger is Apache 2. And previously, I created JSON Hero with my co-founders, which is a JSON viewer. You can go use it for free. And I built iOS apps back in the day. And obviously, I am a nerd, along with all of you. Yeah, so I'll just explain briefly what Trigger is. So it's a background jobs framework and AI infrastructure. So it means that you can easily, inside your code base, write some code, and then we will spin up tasks that can execute for a really long period of time, or short. And you can get those updates into your front end, as we'll show. So these are the things that I think are, but maybe I'll also say that we got very lucky because we built this background jobs thing maybe 2 years ago we started, and it just so happens that agents are the perfect background jobs use case because they run for a long period of time, you want to spin up loads of them, and then you want to get those updates back to your users. Or sometimes you don't, sometimes they're just running. So I'll briefly talk about this, what we think are the 6 pillars of building agents. We're going to focus on this one. But basically, you can run stuff for a long period of time. It's really reliable. So it runs and it has built-in retry semantics and durability, queues. You can install system packages. So often you want to use like Puppeteer to run browsers or FFmpeg to process videos, process documents, things like that. You want to have humans involved. AIs are not super reliable. So you often want to wait and then get humans to approve, reject, or just provide input. And then you would continue processing where you left off. Sometimes there's big delays before humans interact. We'll talk about real time. And then the final thing is just you want to actually know what happened. Like ordinarily when you're running background jobs, you are just like combing through logs which are all interspersed of what happened. You can't tell. So we break it down so each run you can kind of trace through exactly what happened. We'll look at that. But real time, that's the thing I'm going to talk about. So this is how you bring background jobs to the foreground. And specifically, I'm going to talk about not the streaming side of things. I'm going to talk about how you can just kind of get the status of your runs, and then you can like send arbitrary data to your front end. So here's a demo. I wasn't brave enough to do a live demo, but I recorded this about 20 minutes before leaving the house. So here we go. So this is a really simple CSV upload, and it's going to process these emails. So you can see loads of real-time elements here. So we have percentages, we have different batches, we're sending like all sorts of data. You can send like really complicated data from your background jobs. And this is the same view, but in our UI, this is what's actually happening. So there's a parent task here, and then each of those handles CSV rows. That's like a separate server, separate machine executing. So we're spinning up, I think there's like 30 machines here, and you can see exactly what happens. So that's the observability side of things. So this is how you, so first of all, I'm going to explain how you would write your code, and then I'm going to talk about how it actually works behind the scenes. So you throw a trigger folder in your project, and you create a file. Here we have this thing that handles an individual row of the CSV. So there's a main task, which is where you upload your CSV, but then each row, we call this, and then we're processing the row. In reality, you might want to do something more interesting here. Like maybe you take those CSV rows and you run Puppeteer on them, and you scrape websites, like looking up company information or stuff, something like that. But the critical thing here is we're doing these metadata calls. So you can set metadata inside the run, and that will very quickly update rows in Postgres, and we'll get onto how that works. So this allows you to, inside your code, make updates. Then in your web app, from your front end, in this case React, you use our use real-time run hook, and you give it a run ID and an access token, and we'll talk about authentication later. And then you can get the data that we just set. And this will just stream in, like as updates are made, it will appear, and your UI will automatically re-render. Okay, so how does this actually work? So when you call metadata set here, what we actually do is we store those in memory for a little bit of time. Probably, I think it's like 500 milliseconds in case you call this really rapidly. But ultimately, it gets sent to our server, and then we do an update on that row in Postgres, and it just goes into Postgres. In this case, we're also actually completing this run, but you don't have to. You can just make metadata updates. Postgres, that's our live Aurora database. So in your browser, so the other side of things, you might have like hundreds or thousands of users. They're running your web app. That React hook is running. And what happens is we send a request via the Trigger.dev platform, and that's where we do authentication. So we check, like, do you actually have permissions with the access token to access that particular run? If you don't, you obviously get a rejection. If you do, we construct a where clause, which is like a SQL query, basically, and we pass it to Electric. So we have Electric running as a separate service. And then Electric, initially, it does a query into Postgres. So it gets the state in Postgres for that particular run. But this is where the really interesting stuff happens. So as well as returning the run data, we also get a transaction ID back. And Postgres creates what's called a shape. And this is great for performance, because if you have lots of users querying exactly the same data, you keep the same shape, which means you can get real-time updates without having to hit Postgres again. And we want to avoid hitting Postgres because we're doing super high throughput stuff here. From there on in, you get real-time updates. So it actually uses long polling, but you get like super fast updates. Like within like a couple of 100 milliseconds, your UI across all your users is updated. Yeah, what the hell is a replication slot? I didn't know what one was before working on this. I had no idea. Although I knew what logical replication is, which is how you end up with read replicas from your primary database. I didn't know what a replication slot was. So I asked ChatGPT to generate me a diagram. Postgres is the elephant, in case you hadn't figured that out. So when you write SQL and you execute a SQL query, Postgres passes that string. It creates a plan of how to execute that query, and then it executes it. And then if you have made changes to the data, so if you've created, updated, or deleted, it goes into the shared buffers, and then that gets put into the WAL, which is the write-ahead log. If you follow people on Twitter talking about Postgres, you'll hear a lot about the WAL. And then we have Electric running here, and Electric is subscribed to a replication slot. And that basically means that the replication slot is kind of like a bookmark. It's like, where did Electric get up to? So that allows it to basically just keep consuming updates from the database. Like it's just pulling updates all the time from Postgres. And we have a specific limit on that replication slot where we only care about one table in Postgres, which is the run table. So we don't process any other tables, which is really, really important for us. The classic question everyone always asks is, does it scale? Well, we are processing over 20,000 run updates per second. I think it's actually probably a lot higher than this now, but this was a couple of months ago. And we do over 0.5 terabyte of Postgres inserts per day. And so far, we are not sharding that, although we will inevitably have to do that at some point, which I'm definitely not looking forward to. So yes, it does scale. This is like how I think about our users. Okay, so we'll go into some of the details about how we've implemented some of the application side stuff. So authentication is something that we need to deal with, we talked about before. So for that, we use JWTs, so JSON Web Tokens. They're a perfect fit for this because you only pay the cost of a database query once. So you have to check that they're authenticated to create the token, but then you attach all the permissions for the token inside the payload, and then you can verify it's valid or not. So this is a bad example because there's no permissions here, but you can pass in scopes. So you can say, I only want permission for this specific run, for these fields, for like whatever you want. We could have like arbitrary permission levels, and you get amazing performance. So you have to say the magic word. Okay, rate limiting. So because we're dealing with end users, browsers, like their users, you could end up with like 100,000 users hitting this. So we need to protect against that, especially on like the free plan. So the way we do that is we use Redis, and we limit connections based on the plan. So like on the pro plan, you get 500 connections, and you can request more, and we'll give you more. I think we do a small charge for it. And we use the sliding window rate limiting algorithm. If you haven't seen this blog post, there's an incredible blog post at smudge.ai where they talk about rate limiting. It's amazing. It has all these live demos of you can see all the different rate limiting algorithms. Highly recommend that if you ever get into that world. I'm assuming none of you thought you would see any Lua code, but here is how you do a sliding window, how we do it. Basically, all it means is that you only allow X many requests in a 5-minute window is what we do. I won't go into detail. Okay, this was a major mistake we made. So we have this other hook called use real-time runs with tag. So when you trigger a background task, you can attach a tag to it. So often people do like an organization. So they have a customer, they attach the customer ID to this. But the thing we didn't think of was that you accrue runs over time. Like that organization is doing loads and loads and loads of runs, and you end up with 100,000 runs. And then before we added this created app filter, you're going to get all 100,000 runs through, which is obviously not good. Lots of data, lots of processing, and also the user just doesn't want it. So we had to do some time filtering. And this was a bit tricky because we talked about shapes before. So shapes are like a cache, and it means you don't hit Postgres again, but they need to be stable. So we needed to figure out a way of making that created at stable. So what and especially with React, because you can end up in weird situations where like every React render is like doing another query, and you're really in a bad place at that point. So what we do is we basically just cache them. We take the shape ID, which is unique for that particular where clause, and we cache the created at. So when you load the page, you will get that 1 hour window. And then if you just on the page for like a day or whatever, it will still be that same created at date. So you'll get them from that point onwards. It works really well, and it means we've like massively cut down on the number of runs we're returning. And it also behaves how users expect it to behave. They were all very confused about how it worked before. Like, why am I seeing data that's like 6 months old? So finally, I'll talk about why. Why did we choose electric and sync in particular? We were already storing data in Postgres. Like operationally, we need Postgres, and we were writing the data there. So if we chose something else, we would have to write the data somewhere else, and this is a lot of data, so we didn't really want to do that. And as soon as you're writing data to multiple places, like things get difficult. The other reason, which is a really important one, is that we wanted developers to be able to subscribe to a run in the future without having to think about it when they triggered the run. So often you trigger something, and then you want to give your users updates, but you don't necessarily know like which runs are going to have updates. We also wanted, well, actually, this is kind of a performance thing, like why sync? So we didn't want to do WebSockets, and that's because we've been burnt in the past by WebSockets. Like we'd use WebSockets in a previous version of the product. It was incredibly hard to scale. We just had all sorts of problems. It cost loads of money. It was a nightmare. Like if you're trying to build a really high scale system, I really highly recommend you don't use WebSockets. Like use SSE, like use something else. And we also wanted like really fast updates. Users, like you want something to happen in your background task, and you want the update to be like in your front end immediately, which basically rules out polling. So you can obviously poll like really frequently, like every 50 milliseconds or something, but you end up hammering your resources if you're doing that. Like you will hammer your Postgres database, or you'll hammer whatever you're hitting. So it becomes really problematic. So yeah, that's why we chose sync and why we chose electric. So finally, Trigger and electric. Yeah, it's been a great experience. And the team, I just want to shout out the team as well, have been really, really good. We have, I think, pushed it very hard. And probably, if we're being honest, like our use case is not really what it was built for doing. It's not really like a pure local first use case, but it is coped incredibly well with demand. Thanks. Does anyone have any questions? Sure. Yeah.
No, check. Um, oh yes. Yeah, and the big problem I had is, so basically I get the CSV. I then oh yes, that was my first question. You said you spin up multiple machines. So if I have a CSV with 6,000, what are you doing? Are you chunking it and then passing it to lots of celery tasks?
It's entirely up to the developer. In the demo, we just loaded a CSV. By each line, we just run another task, and each task is run on a separate dedicated machine. So you do like 250 meg RAM or something on that, and then we reuse them when the runs finish. But yeah, you can spin up like thousands of machines at once, or I think if you were building this in reality and you were dealing with like 50,000 row CSVs, I wouldn't do that. In fact, please don't do that if you're doing that. You would like batch it basically, and you would like do 100 rows at once or 200 rows at once.
Okay.
Yeah.
That's cool. That's kind of what I do. And the next question is, and then so I batch them into 50. I pass each at the moment to a celery task, but you give me a good idea. And then I deliberately chunk them into 10 because to save on transaction costs. So that was going to be my next question is, when you have these sessions which are open to Postgres, how many transactions are you making for these small kind of binary updates?
You're talking about on. So the question was about how many updates are we making. So are you saying when from our side when you're calling those metadata set updates, how many are we dealing with?
So,
or are you talking about from the user side if you were building your CSV parser?
So I get charged per transaction to the database.
Okay.
So I want to keep it as low as possible, which is why I commit in chunks. So I guess my question is, how does that work?
Again, it's up to you as a developer how you want to structure it. If I was building that, I would do batches and I would commit at all at the end and just do one Postgres connection. I mean, it's a serverless product. So if you spin up 1,000 machines, and they're all running, you're going to have 1,000 connections to your database potentially. So you have to think about that.
With electric, again, how does that work?
Okay. So when you do this, I'll go back one more. Too distracting. When you do this kind of thing, you don't need to worry about that because it's all on our side. So we handle flattening that into like a single atomic update, and like we host, like we run all of the software and hardware for that. So you don't need to worry about the number of connections. I couldn't actually tell you how many it is. I don't think the metadata updates are like a very significant performance problem.
Another question. I guess the metadata at that point does not get passed to Postgres itself. Metadata is only used within your system.
The metadata here is it's in memory, which is why you don't await it, and then we flush it, and then we do an API call at that point. We send it to our server, so the Trigger.dev servers, and then it goes into Postgres. So if you're doing lots of these over like a period of time, you will end up updating Postgres a lot. Yeah.
How are you implementing the sort of retry or durability behind the scenes? Are you like checkpointing the state of the JavaScript runtime, or are you doing like a replay approach? How does that work?
Yeah, it's a good question. So we've actually built a few versions of this. The previous version we built was basically we were just serializing data, and you had to use strings to like define steps. But right now we actually do a snapshot of the CPU and memory of the running machine using a technology called Creo, which is checkpoint restore in user space, which is a Linux feature. And then we can basically pause, and then we can resume later. And retries are basically, it will rerun, re-execute the function from the top. And you can use idempotency so you don't execute the same thing twice.
Thank you.